Am I audible? Hello? Hello? Am I audible to all?
Yes, sir. Audible, sir.
Okay, thanks. So let's get started for this class. So hello everyone. Uh, I am Himanshu Mishra and I am the PhD research scholar in the Department of Applied Mechanics. So today I am going to solve questions which are related to the heat generation, critical layer, and the transient heat conduction. So last week I have briefly solved some Simon practice problem related to the basic conduction, and today we will move to the heat generation and the transient heat conduction. So before moving to those topics for this week, I will like to go back to the previous week and revisit one problem which I have briefly discussed about the boundary condition in the two slab. So in the last week, I have drawn a two slab 1 and 2, and I define the boundary condition in this two slab at the interface, saying that the temperature gradient should be equal at the interface and the temperature also should be equal at the interface. So there is a little correction that if the interface is very smooth, we will have the boundary condition as I discussed before, that the temperature should be equal at the interface and the slope should be equal as well. But if there is a contact resistance, suppose the interface is not smooth, in that case the similarity of the temperature at the both side will not be there, and there will be difference in the temperature. So let's say if there is any contact resistance and the surface is not smooth at all, then there will be some temperature drop within the contact of the two slab. So this is my TA, let's say, and this is my TB. So yeah, so this is I want to make some correction from the previous week because I did not discuss about anything about this contact resistance. So moving to this week topics, let's discuss for our first question. So the first question is about to identify the correct statement. So the statement A says that the uniform heat distribution is one of the assumption in the lumped transient heat transfer. So in the this is a correct statement actually. So in the lumped heat transfer analysis, the first assumption to to be considered is the uniform heat transfer, which indirectly says that. So to do the lumped heat transfer analysis, we need to ensure that the Biot number, which is the ratio of the internal conduction resistance to the external convective resistance, should be less than 1, or to be more specific, should be around at order 0.01, which says that inside the body the heat should be uniformly distributed. So in other words, the thermal conductivity of the body should be very high, so that whatever the heat you will provide at the surface of this body, it will be quickly uniformly spread within the body, and this can be indicated by the Biot number, which is less than 1, which the value of the Wyatt number is very less than 1. For example, let's say you have some whenever you warm the food in the microwave oven, after some time when you take that food out, you may found that the food is hot from the boundary, but it is relatively cold at the center. This indicates that the heat does not uniformly distributed around the food, which makes its Biot number around of order 1 or even the greater than 1. In such cases, you cannot use the lumped heat transfer analysis. So overall, the lumped heat transfer analysis, before you writing down the equation, you need to ensure that the conduction of your body, whatever, if it is the solid body or you consider any food in a problem, the conduction of this should be very high. Thermal conductivity should be very high of the body to ensure the uniform heat transfer across the body. So yeah, so statement A is the correct statement. Now the statement B says that more surface area of the body, more quickly it attains the surrounding temperature. So let's analyze with respect to the heat lumped analysis. So So as per the theoretical model, we know that the transfer of heat, variation of the temperature is actually depends on the heat transfer coefficient, surface area, volume, and the heat storage capacity. So if I increase the surface area of any body, my value of B will be increases, which ensure that the temperature distribution will be very quickly with respect to time. So for example, if I draw the curve, if I plot this equation in time, I will found that this curve will attain the surrounding temperature T infinity. Let's say this T infinity is my surrounding temperature. So as I increase the value of B, so I am increase the value of B from this surface area, because I am increasing the surface area, so my value of B getting increases. So if I increase the value of B, the body will attain the surrounding temperature much quick, and therefore this B statement is also true, that more the surface area, it will attain the surrounding temperature much earlier. So we can deduct many conclusions from this statement, like if we increase the overall volume of the body, the value of B get decreases, and therefore it will take more time to attain the surrounding temperature. Similarly, we increase the heat transfer coefficient H, again the value of B increases and it will quickly adapt the surrounding temperature, and so on. So any doubt in this question? Okay, so let's move to the second problem, second numerical problem. So in this problem, there is a plane wall, is a composite of two material A and B. The wall of material A has the uniform heat generation, having a thermal conductivity thickness, and the wall B has no heat generation with specified thickness and thermal conductivity. The inner surface of material A is well insulated, while the outer surface of material B is cooled by water stream T infinity and have some thermal coefficient. So we need to sketch the temperature distribution and to determine the temperature T naught. So we have a wall. So let's say this has material A and this has material B, and here I have a temperature T naught and this side is insulated. And at the outer surface of material B I have a water stream having the temperature of T infinity 30 degrees Celsius. So first we need to determine the temperature distribution from, let's say, point x naught to this x infinity. So for temperature distribution, here in this wall we have a heat generation, and in this wall we have only heat conductions. And here, let's say at region C, we have a heat convection problem. So the temperature distribution in all three region A, B, C will be different. For example, in region A, since we have a heat generation in the problem, the temperature distribution will be actually depends on the square of the thickness of this slab A. So there will be parabolic there will be some parabolic temperature variation here. So temperature will increase first because there is a heat generation at the left side of the plane slab. Upon reaching at the slab B, there is no heat generation in the slab B, so there will be temperature distribution will be linear in the slab B because the temperature is just heat is just transferred due to the conduction. So here there will be the linear temperature variation, and at the edge B where the water stream is flowing on, there will be the huge drop in the temperature due to the convection. So first there is a little increment of the temperature there will be little increment in the temperature due to the heat generation, and this will be parabolic, and upon reaching at B it will be linear decrement of the temperature because there is no heat generation, only convection, and due to the convection there is a huge drop in the temperature difference, and after some time far away from the body it will remain almost the variation will become constant, so the temperature will attain the T infinity very slowly. So this is my temperature variation with respect to x. Now the second problem says that to determine this temperature T naught at A. So we need to determine the temperature T naught here. So for plane A we can write the equation like so since we have a heat generation, the temperature distribution will be governed by this equation in plane, or I should write in slab A, whereas the temperature distribution in region C will be so I have a T naught at the left side of A. Here I have T1, here I have T2, and this is my T infinity. So let us first find temperature T2 and then temperature T1, and then we can use this equation 1 to find the temperature T0. So for temperature we have already given the temperature T infinity, so this is my T infinity. So we can find the temperature T2 from this equation. So when I solve this equation, I will get my temperature T2 as 105 degrees Celsius. So I get my temperature T2. I know T infinity. Now I will find the T1. So for temperature T1, I can use so RB and RH is my resistance. RB is the resistance of the slab B, and RH is my convective resistance. So RB can be given as LB and KB, and RH given as 1 by H. So from here I can from this equation I can find my temperature at the interface between slab A and slab B, which is we just need to substitute the value of heat transfer coefficient, thermal conductivity, and so on. So we will get temperature T1 as 115 degrees Celsius. So now we know that temperature T1, T2 and T infinity, and we can easily find T0 from equation 1. So on solving this equation, I will get my temperature T0 as 140 degrees Celsius. So what I have done, we have given only temperature T infinity here. So we first find T2, then we find T1, and then we find T0. So for finding T2, we use this relation since there is a heat generation, and for to finding the T1, we use the previous Fourier heat conduction relation here. We can also define this. We can also find by putting T2 here instead of T infinity. So we just record only this resistance. But anyway, there are multiple ways. And for T0, we use this relation, which is the heat generation in the slab. So, yeah. Any doubt in this question? Okay. So the third question is to derive the critical thickness of insulation in the spherical body. So we know that the critical thickness is a concept where we add the extra thickness to the body, and even we add the extra insulated material to the body, it will increase the heat transfer up to some certain thickness, and that thickness is called the critical thickness. So to be plotted, the uh, heat transfer first increases as we increases R. So this is my heat transfer Q, and this is my heat let's say distance in the radial direction, or in the spherical in the spherical geometry. So first the heat transfer increases as we add the insulation outside the body. Then it becomes stable, and then start decreasing as we keep increasing the thickness of the outer layer of the outer layer of the body. So critical thickness is this maximum heat that increases. I mean, yeah, maximum heat increases as we keep increases the thickness of the body. So at here we know that the slope is 0. That means, that is, to find the critical thickness of insulation, this slope should be 0. And from the Fourier's law we can define Q as so this is my convective resistance. This is the resistance of the insulation that I am keep adding, and this is the resistance of the spherical body. Now we can evaluate this to be 0. So we need to differentiate this expression with respect to R here, and on taking the derivative of this expression with respect to R and equate it to 0, we will get the critical thickness as 2K by H for the spherical body. We can do the similar exercise in case of the cylindrical body, and in that case we will get K by H. So yeah. Any doubt until now on any question? So moving ahead, so the next question is to consider a heat situated inside the hollow sphere made of aluminium. Thermal conductivity is defined. The surface temperature of the inner wall is 250 degrees Celsius. The sphere is externally insulated. The ambient temperature is 20 and the heat transfer coefficient is 30. So we have to find the thermal conductivity of this sphere. So we have given the heat rate and property of the material as well as the thickness of the material. So here we can use the Fourier's law, which is given by, so R total is my total resistance. I can expand this expression into so we need to substitute the given value into this expression. we need to evaluate K1. Q is given as 80. So on solving this, we can evaluate this K1 as 0.062 watt per meter Kelvin. So any question until now? So there is no heat generation, just we need to use the Fourier's law in the spherical geometry. That's all. And the assumption is defined as a steady state, one dimensional, and the constant properties, and so on. So it's just a basic Fourier's using use of some Fourier's law. So let's move to different question. So consider a medium in which the heat conduction equation is given in its simplest form. So we have given this equation, and based on that we need to choose the correct option. So the first option says that the equation describes a steady two-dimensional heat transfer with no heat generation and the variable thermal conductivity of material. B is the equation describes the transient one-dimensional with heat generation. C is steady two-dimensional heat transfer with no heat generation and the properties are constant. Again, transient two-dimensional, no heat generation, and properties are constant. So anybody can want to tell what should be the correct option in this case? So we have given the equation. You just need to look the equation and describe the equation. That's all. Anyone can guess what the equation is telling us? What is the nature of the equation?
Sorry, it is B.
So we have two options, B and C. Okay, and okay. So let us verify one by one. So first consider the option B. The equation describes transient one-dimensional heat transfer with heat generation and thermal conductivity of the material to be constant. So first of all, there is no variation in the properties, there is no variation in the thermal conductivity because the thermal conductivity is separately written at the RHS, and it is to be the constant. Moreover, the equation is written in terms of x and y coordinate system. That means this equation is not two-dimensional. So in B option, it is given the one-dimensional heat transfer, but there is a heat transfer in the x direction as well as in the y direction. So we can remove this B option because this equation is in written in two-dimensional version. So we have now C and D option according to the options you guys have selected. So the equation describes steady two-dimensional heat conduction, no heat generation, constant material property. So these are correct points, like the properties are constant. Yes, there is no heat generation. Yes. So equation is two-dimensional. Yes, but this equation is unsteady. So we can see that the variation of temperature with respect to time is non-zero. So this is a unsteady heat transfer equation. So we will have option D as a correct option, which describe the transient two-dimensional heat transfer with no heat generation, and yeah, of course the properties are constant. Yeah. So let's move to the question number 6. So a person is found to be dead at 5 p.m. in a room whose temperature is 20 degrees Celsius. So this is my room temperature, I guess. The temperature of the body is measured to be 25 degrees Celsius when found, and the heat transfer coefficient is estimated to be this. Modeling the body as a 30 centimeter diameter, 1.7 long cylinder, and estimate the time of death. So we need to estimate the time of death of the person. So this will be the rough calculation, not exactly what the officials are doing. I mean, as of now. So from the question we know that this is a question for from the transient heat conduction, because we have given the properties of the body, temperature, and we need to estimate the time. So the initial temperature we have given the surrounding temperature, and now we have to find that when we measure the temperature after some time, what would be the temperature at that whenever we measure. So we use the lumped heat transferred analysis in the problem, and the lumped for that the equation can be written as so this is my equation of lumped heat analysis. So as I said earlier that before we use this lumped heat transfer analysis, we need to make a very solid assumption, like the body should be, the conduction inside the body should be uniform, or the thermal conductivity should be very high. Now do we have given H. Okay, so let's say the thermal conductivity for the body is given as 0.617 watt per meter degree Celsius. So first we need to check whether there is a uniform heat transfer or not, and we can do this by a Biot number. So if my Biot number would be very less, then it is then we can use this lumped heat transfer analysis. But in this problem, the Biot number is roughly around equal to actually it has the order of around 0.1. So this is a rough estimate of this calculation. So okay, let's use this equation so we can find the value. So here the value to get this value of B, we need to find the surface area and the volume. So we can define this by some characteristic length. So we can define like is volume so we can model the body as a long cylinder. This is again very rough assumption. So on substituting the value we get so we can, on solving this, we can get the characteristic length as 0.0689 meter. Now we can use this length to find the value of B. Sorry, this would be 1 by LC actually. So 1 by LC. So we can put the value here of this property of the bodies. believe P would be around 2.79 second inverse. Now the ambient temperature is 20 degrees Celsius, and the temperature is found when the body is found, the temperature is 25 degrees Celsius. So the ambient temperature is my 20 degrees Celsius. Yeah. And when body found, it was at 25 degrees Celsius. And the initial temperature is around 37. We know that this is a normal human body temperature when alive. And we need to find the time, rough estimate of time of the death. So on solving this, we can find time as 12.2 hours approximately. Yep. So any doubt in this question? So moving ahead, plane wall of thickness 0.1 meter, thermal conductivity 25, having a uniform volumetric heat generation of 0.3 megawatt per meter cube, is insulated on one side while other side is exposed to fluid at 90 degrees Celsius. The convection heat transfer is this. Determine the maximum temperature in the wall. So yeah, this is a similar question that we have solved just now. So we have a slab, again we have insulation, we have temperature T naught here, let's say it defines temperature T naught here. There is a fluid here having thermal coefficient H and some surface temperature Ts and T infinity here, which is 92 degrees Celsius. And we have defined K and H in the question, and we know the volumetric heat generation as 0.3 megawatt per meter cube. So again, we know that for the slab we can use the equation like QL square 2K plus Ts, and for the fluid area we can use the equation QL plus H. So the similar problem we just solved before some in the question number 2 we have solved a similar problem. So the derivation would be the same. We need to find the temperature Ts first, which can be given as temperature Ts would be then 152, and then once we got the temperature Ts, we can find the T naught. Conductivity is 25. So we will get temperature T naught as 212. So we use the same approach. We have given T infinity, we find first the temperature Ts and then T naught. So this is relatively a simpler problem that compared to the problem we have solved earlier, where we had a two slab and there was a water stream flowing at the right of the slab B. Here we have only one slab and some fluid. So yeah, it's a similar problem. So let's move to the next question. So radioactive waste are packed in a thin walled spherical container. The waste generates thermal energy non-uniformly as per this equation, where Q naught is the local rate of energy generation per unit volume. Q naught R naught is the constant and the radius of the container respectively, and we have a temperature of the coolant as T infinity and having the thermal coefficient H. So we need to determine the temperature distribution TR. So okay, so this is the heat generation problem, and we have defined the generation of heat in some as a function of the radius of the container R. So to define the temperature variation of the temperature, we just write down our usual differential equation with the heat generation for the cylindrical geometry, which can be given as 1 by R square. So this is my one-dimensional equation with heat generation. Of course, the equation is steady because there is no time dependence on the equation. Otherwise, we on the RHS we will get some term like dou T by dou R or 1 by alpha. But this term is zero in our problem in this problem. So yeah, on solving this equation, we can get. So we need to integrate this equation. So on integrating first time, we will get dt by dr some constant. So here I substituted the q as a function of some radius which is given in question. So q actually given as q dot is actually given as q naught so I put this expression here and then I integrate to get this equation A. Now I can again integrate the equation A to get the temperature distribution as a function of radial direction, properties and some constants. So if I again integrate the equation, I will get I can put this R square here and this dr I can substitute at the right side. Yeah, so on integrating I will get this relation. Plus C2. So now in order to find the constant C1 and C2, we can use the boundary condition. So the boundary condition will be here dt by dr at r equals 0 means here will be 0. So there will be no slope of this temperature gradient in the radial direction will be 0. The other boundary condition we can use at the interface. So in the last class I discussed that if we have multiple modes of heat transfer like convection and conduction, then at interface we can use the both modes of heat transfer as the boundary condition. So we have here convection heat transfer, and here the heat transfer take place due to conduction. So at boundary, this at the end, the boundary of this surface, this cylindrical body, the boundary condition will be at, this is my R naught equal to, so I have a two boundary condition, this and this, and I have a two constant, this and this. So from this two boundary condition I can get the constant. So by using, let me write this. So this is my boundary condition and this is my boundary condition. I use these two boundary condition to evaluate C1 and C2. So after finding C1 and C2, I can write my temperature distribution as so this will be the temperature distribution we will get after finding the C1 and C2. So any doubt in this question? So in this question, yeah, okay.
No, sir.
Okay. Yeah, so in this question, we had heat generation and we just used the differential governing equation, the conduction, to evaluate the temperature distribution in the radial corner. And we had a boundary condition in form of convection. So using that boundary condition, we just found the constant. So yeah. So moving to the last problem. So consider a plane wall of thickness L whose thermal conductivity varies linearly in a specified temperature range, which can be defined in like this, where K0 and beta are constant. The wall surface at x equals 0 is maintained at constant temperature T1. At L it maintained at T2. Okay, this one nothing. Assuming the study one-dimensional heat transfer, obtain a relation for the heat transfer rate through the wall and the temperature distribution. So we have a plane wall and the thermal conductivity is varying according to the relation K0 1 plus beta T. Here beta is the constant. There is no heat generation and the heat transfer is steady. So we can just use the Fourier's law to evaluate the heat transfer rate. So this will be the heat transfer rate. Now we need to evaluate this K average. So since the thermal conductivity is not constant here, and it depends on the temperature distribution, so we need to define the average thermal conductivity of this slab. And to define the average thermal conductivity, we have to take the average of this thermal conductivity at different temperature location, at temperature at location 2 and at location 1. So here the temperature is T2 and here is the temperature T1, and here we have some thermal conductivity which is, let's say, KT1, and here the thermal conductivity will be different, like KT2, and we need to take the average of this thermal conductivity at considering both the location 1 and 2. So this can be written as K2 minus T1 So this will be the expression of k average. So we can integrate this expression k naught. Since beta is the constant and k naught is constant as well, we can write outside the integral and then we can evaluate. And on solving this, we can write so this will be my k average, average thermal conductivity, and I can use this expression in the Fourier's law here to find my heat transfer rate through the wall. Now to evaluate the temperature difference, I can again use my Fourier's law. So we know that the thermal conductivity will be vary according with the temperature. So thermal conductivity is a function of temperature. So we can integrate this to get the temperature distribution. Let x naught is 0. So we can substitute this well expression of k naught as k as this k naught 1 plus beta t. So after integrating this expression, we will get qx so here t minus t1, here t square minus t1 square by 2. So yeah, so this will be my expression after integration. So we already know the expression for q, which is given in terms of k average. So we can put this expression of q into expression, let's say b t2 minus t1 yeah, and then we can solve for this T, which is the distribution of temperature in the slab. So we need to find the T here. X by L AK T plus AK naught T1 plus beta minus beta AK naught here putting this at the left hand side, we can obtain oh, we have a t square here also. So putting this and this expression on the left hand side, we can obtain t square plus 2 by beta t plus k. So this will be my temperature distribution here for this problem. So this is a quadratic equation, so we can find the roots of this equation. So after finding the roots, we can just write the expression of t as some polynomial roots of this equation, which will be some complicated function of 1 by beta plus some under root. It will be 1 by beta square and some function of k, t1, t2 and so on, like this. So any doubt in this question? So in this question, the conductivity will vary according to the temperature. So we first find the average thermal conductivity then, and using the average thermal conductivity and the Fourier's law, we define the heat transfer. And then we solve, again use the Fourier's law. Since it is a first one dimension study problem, so we can directly use the Fourier's law instead of using the differential equation of the conduction and so on to get the temperature distribution. So that's it for today. If you have any
Thank you very much, sir. Please, sir, can you able to show the first slide, sir? The first one and second one.
Okay.
That's why I want to note it up.
This first slide.
Yes, yes, sir. Okay, sir. Second and third.
Is it fine?
Okay, sir. Thank you very much, sir. Thank you.
Thank you then.
Thank you, sir. Thank you.